Hello and welcome. In this video we will look at encryption on Android, how it works, where you will see it, and how to recognize common patterns. We will compare simple cipher like cipher to a modern AES, and also we will have a peek at a library-based encryption that you may encounter in real applications. Encryption is a process of transforming readable data, plain text, to unreadable data, ciphertext, using a specific algorithm and a secret key. Without the correct key, encrypted data cannot be decrypted back to its original form. Encryption is mainly used to protect data from unauthorized access. There are many encryption methods, from very simple ones to advanced cryptographic standards. Some examples of encryption are Keyser cipher, AES, and RSA. Let's start by looking at the sample code I've created. Here we have encryption algorithms class. The first encryption utility is Keyser encryption. The idea behind the cipher is very simple. It uses a number called shift to transform letters and sometimes numbers into other characters based on this shift. For example, if the shift is 3, the letter A becomes D and the number 1 becomes 4. This method of encryption is extremely simple and therefore it is very easy to recognize and decrypt it. I've added it to my demo just to show it to you as an example. It should never be used in production applications, although in my experience I have seen this cipher in a low quality Android applications. Next, we have the AES Encryptor utility. AES stands for Advanced Encryption Standard, and it is a modern encryption method which is considered to be the current standard for secure encryption. It uses a key and IV, initialization vector, as parameters to encrypt and decrypt strings. Now let me show you how encryption works in my main class. We have a sample string here, it's a Wikipedia URL. We will encode and decode it using both of our encryption methods and then check the results in the logs. So let's launch the application and take a look. As you can see, Keyser encryption is quite weak since we can still tell that it is a URL just by its structure. Yes, the cipher could be improved to include characters of all types, but it would be still recognizable for an experienced reverse engineer. If you look at the AES encryption results, they appear much stronger and more secure. We cannot understand anything from the encrypted strings. I've shown you examples of both encryption and decryption. However, when reverse engineering applications, you will typically see already encrypted strings and the method to decrypt them. So to give you an example close to real-world scenario, I've created a sample application with some simple encryption logic. I haven't used obfuscation here to keep everything clear for you, but keep in mind that developers, especially malicious ones, will try to hide something and the code will usually be obfuscated and encrypted at the same time. So here we have a main activity class and let's take a look at it. We can see two methods that handle the logic of setting text in the text views. The strings being set are actually the results of methods from another classes. Let's follow one of them. When we open that class, we can see several strings, all of them encrypted. And notice that they are all passed to the decrypt method of another class. So let's open that next. Once we do, we can see the full decryption class logic. Once again, in a real-world scenario, the code would almost certainly be obfuscated, and we wouldn't see the class name as clear as here. However, even if the class name was hidden, we could still understand it's related to decryption. Its method is used for multiple encoded strings, and we also can see the logic involving numbers and symbols, which is a strong indicator of decryption functionality. For an experienced reverse engineer, even without the class name, it would be immediately recognizable as Keyser cipher, mainly because of this line. The mod 26 is a clear sign of Keyser cipher logic, since 26 is a number of letters in an English alphabet. And here are two ways how we can proceed in this case. First, let's just open our browser and find Keyser cipher decoder. We copy any encrypted string from the code, and then we also notice the number 7, which indicates the shift. On the website, we choose the decode option, set the shift to 7, and paste our string. And here we are, we can see the original string, which is a URL. The second way to proceed with decryption, which would also work for any weak or poorly implemented encryption method, is to recreate its logic in our local environment. First, we proceed to JADX and fully copy the class responsible for decryption. We return back to Android Studio and paste all this code there. However, you can see some errors because the compiled code often uses some synthetic methods. However, we can easily fix it manually. In this case, we just need to remove the $default part and change some arguments passed to the method. If you are not sure how to fix such conflicts, you can always ask AI helpers to do it for you, and it's completely normal practice. So now our class is ready to be used. So we proceed to main activity, and just inside the onCreate method we call the decrypt method for our new class. The arguments for decryption we take directly from JADX. Let's copy them from the first method call. And of course we need to put the output to the logs so we can see the result. Now we are ready to launch our app and check the output. Let's start it. And as you can see, we successfully decrypted the string again. We can repeat this process for other strings. Let's do it to see them all. In a real world scenario, there may be hundreds of such strings, and it would take a lot of time to copy them manually. For such situations, some scripts may be used to extract multiple strings automatically, but that's a topic for a separate video. For now, we will copy them manually. So we are now ready, and after launching the app again, we can see all the strings successfully decrypted. This method works well when the decryption mechanism is weak or implemented insecurely. There is one more way of decryption, and it is actually one of the most reliable ones, and it's using Frida. However, we will cover Frida in following videos, and now it's just for your information. Now let's consider another decryption class that we have in our sample APK. We proceed from main activity to the class that uses it, and we can see that it decrypts strings using another helper class. We proceed, and from the name we can see that it is AES Encryption. However, we could also understand that even without the name of the class, since in the body of the decrypting method we can see the usage of AES related strings and functions. AES is a standard encryption method, and if it is implemented correctly, it's practically impossible to decrypt it. However, here I've made an example of bad implementation, so we can immediately see the key. Having the key, it becomes easy to decrypt AES if you understand the process. To decrypt it, we will use a very powerful tool called CyberChef. It's an open source tool that allows you to perform different operations with strings and files, including encryption, encoding, and much more. Before we start, I have to quickly explain you how AES encryption works. It requires two main parameters, the key and the vector. The key is the secret password that both sides must know. It's used to lock and unlock the data. Without the correct key, you cannot read the message. The vector, which is called IV, initialization vector, acts as a random starting point. It ensures that even if you encrypt the data twice with the same key, the results will be completely different. Then AES takes your data, such as text, files, or passwords, and transforms it to an unreadable code using several rounds of substitution and mixing. The result is called cipher text, which looks like random characters. When you want to read it again, AES uses the same key and vector to reverse the process and get your original data back. So to decode AES, we will need the key and the initialization vector. To get the IV, we take any encoded string and extract it directly from the bytes. In my implementation, you can see that before all operations, the encoded text is base 64 and decoded, and the IV is the first 16 bytes. So we copy an encoded string, open browser and search for CyberChef. We open the official page and wait for it to load. CyberChef is extremely useful tool for reverse engineering and string manipulation. To build the recipe, we search for from base 64 and drag it into the recipe field. The IV will be the first 16 bytes or 32 characters, so we copy that slice. Next we search for AES decrypt and add it to our recipe. We paste the copied IV into the IV field and set it as base 64. As you remember, the key is present in the code, which is actually a bad practice. So we copy the key and paste it into the key field using UTF-8 format. CyberChef will output the decoded string. The initial gibberish bytes you can see is the IV, and the remaining bytes are the visible plain text. On the other hand, we can also repeat the process locally like we did with Skizzer example. Let's copy the AES decryptor class from JADX and create a custom Java class with the same name in Android Studio. In this demo there are no conflicts, so we can launch the code straightforwardly. Now we are set. We launch the app to check the logs. And as you can see, all strings are successfully decrypted. So that's how encrypted strings may be recovered from reverse engineering perspective. The examples above show you bad practices, which makes it relatively easy to decrypt the sensitive data. The best practice is either to use Android key store or to perform server-side decryption when it is possible, so no secret is present in the client side. Okay, now let's move further. As you remember, I have said I will show you 3 encryption methods, but actually showed only 2, Keyser and AES. That is because the third method is more specific. It is done via an imported library called StringFog from GitHub. With this library, you write strings in your APK normally, and the library transforms them so they are stored encrypted and then decoded at runtime, typically using lightweight operations like XOR. Let's check on an example. I created a sample application with several hard-coded strings across multiple classes and added StringFog dependency in build Gradle. After decompiling the APK in JADX, we proceed to main activity and see that the strings are now obfuscated and encrypted. All strings across the classes were automatically transformed by the library. This library is fairly common to make static analysis harder, but it's not fully reliable. You can usually decrypt its strings by copying the library's runtime decryptor and running it locally, like we did before. Or you can do it even easier by intercepting it with Frida. In practice, StringFog is used more as an obfuscation layer than the cryptographic protection. Combined with the code obfuscation, it raises the bar, but it should not be relied on to protect critical secrets. And that's it for encryption, protecting data with keys, from simple ciphers like Keyser to modern AES. If you like this video, please put your like and subscription and leave your comment if you have any questions or suggestions. Thanks for watching, see you in next videos.